Hello there, did you know that you can find area under the curve just by using randomness? Well, most often the randomness is associated with negative feelings when the weekend plans are ruined by bad weather, or Bitcoin is still going up but you have not yet bought it. But if used correctly, can solve different kind of complex problems where traditional deterministic approaches just take either forever to solve or are too complex to implement. One of such problems that we can solve is integral calculations. You can remember from calculus probably that you have spent a lot of time writing down all the equations on paper, solving just to find this one tiny number, which actually was area under the curve. And now imagine that we can just take this paper, rip it apart, throw it away, and use randomness to find the answer. Let's jump in and see how we can do that. Probably I will regret starting with this slide, but please wait, stay. We will demystify everything and it will be very simple to understand. So instead of me trying to explain this equation, let's go other way around. Let's build this equation. Let's start from scratch, from the basics, and understand step by step from where it originates. Let's look at the most basic curve, a constant. It's a flat line with some constant value at each of the x values. So without any complexities, if I would just ask a 5th grader what is the area of this curve, he would quickly spot it's a rectangle. It has some width, it has some height, and we can just multiply those to get the area. So starting with width, it's just a distance between 2 points, from x0 to x1. And we usually call such difference delta x. As for height, it's a distance from 0 line till the function. As function is constant, it is always with the same height. Any function point will be the same. So if I take a value at the start of the interval, it will be the same as the end of the interval, as are a constant. So to calculate the area of this rectangle, I just need to pick any function point and multiply it by the delta x, the interval length. Okay, let's make things harder. Let's use a step function. So for first half of the interval, it will be some constant c1. So for second part of the interval, it will be some constant c2. And I'm pretty sure that you already understood how we can solve that. Instead of one rectangle, we can take two. So one will be for the first half of the interval using the constant c1, and another one will be for the second part of the interval using constant c2. Now that we have two rectangles that are two different areas, we can just sum them together and get the total area of our curve. And you can imagine we could continue. We have 3, 4, 10 steps. So to generalize this formulation, we can use a summation symbol. Basically, it means that from 1 till n, meaning how many rectangles we have, let's sum up together those areas where we take a function value at that rectangle, multiplied by its width. Whoa, a wild challenger has appeared. You can see the situation is pretty similar. We have two different kind of function values at different ends, but now we have some sort of slope. And we could try to apply the same principle and use two rectangles to estimate the area. But now you can see that we are overshooting our function. So we are introducing some error. We are taking more area that is really under the curve. What will happen if we start to increase the number of rectangles? You can see that we have reduced the overshooting part because the rectangles now are smaller and we have smaller section that is going over the curve. Let's again double it. So it means by increasing the number of rectangles, each time we're getting better and better number. Converging more closer to the real result. And that's where limit comes in. So limit is basically saying, if I will keep increasing this segment count to infinity, what would be the number I will start to reach? And that's the integral. And now I hope that this complex function just became much simpler to you. But of course, in practice, it will not work because we cannot do infinite steps to calculate something. That's where the analytical approaches come into play when we're using the table of integrals, calculating with pen and paper to find exact solution. But I have two problems with that. I don't want to sit whole evening solving different complex integrals on paper. It will just take me forever. And second one, there is actually some problems that cannot be solved analytically. And for such problems, we still need to get some result. Of course, it will not be exact. And that's where numerical methods come into play. Instead of calculating exact analytical solutions, we use approximations. We can perform close enough calculations that will be fine for our use cases. So let's look at 3 classical methods that can be used to approximate integral value. First one is the Riemann sum. So it derives directly from the equation that we just observed. So instead of taking infinite small steps, we take large enough amount of steps. But we could also use something else instead of rectangle. For example, trapezoid. Trapezoids try to take into account the shape of our function. While it's still simple to calculate the area, you can see that it requires much less segments to get better results. And third approach is to use some different function to approximate our complex function. So for example, I could break down our complex function into multiple parabola segments. And for parabola, it is quite easy to calculate the area. All of these methods can be used to produce a quite good result. For some, it just requires more iterations. But today we're not here for such kinds of computations. If you're interested in such, leave a comment. We can create a follow-up video if you want. But today we want to use randomness to solve this complex integral problem just by picking random numbers. And this method is called Monte Carlo Integration. So again, let's go over step by step to build up the intuition. We have some sort of function that we want to find the area under the curve. So instead of slicing it into the different shapes, let's draw a rectangle around it. And a rectangle is the most basic shape that we can use. To calculate the whole area of this rectangle, we just multiply one side to another. And now here for the random part, we start to sample random points inside of this rectangle. It is like throwing random darts and seeing where it's landing. If it's landing under the curve, we mark it as a green one. If it's landing above the curve, we will mark it as the red one. And now let's keep sampling, keep throwing these random points and count how many of them land under the curve. When we have sampled enough points, we can calculate the probability of our point landing under the curve. We just take the number of times it was under the curve against all the samples. So we can divide those numbers and get 40% chance of our point landing under the curve. And basically what it means that 40% of whole rectangle is under our curve. And now we can take this ratio and multiply by the area of the rectangle to get our integral. And of course, by increasing the sample count, we drastically reduce the error. Okay, Edgar, so you can stop talking now. Let's go coding. So our goal for today will be to find area of given function in given interval. For example, let's take a sine wave and move it up by one value. And we want to integrate an interval starting from 0 till 2 pi. So let's generate linearly spaced points between a and b. For example, let's take 100 points and calculate y values at those. And let's plot our function. So this is the function that we want to integrate. So you can see that it's just a sine wave which has no negative values. We have moved it up by 1. So now let's define a Monte Carlo integration function. So first of all, we'll pass a function that we want to integrate, a given interval in which we're interested in. Then we also need to provide function minimum and function maximum for enclosing rectangles. So we need to know how high it is and how low it is. And of course, number of samples. For example, let's put it by default 100 or something. Now that we have input parameters, we need to sample random points inside of our bounds. So for the x values, we can use NumPy's random uniform from A to B, provided that we need 100 points. And same goes for y values. We can use uniform sample points between minimal function value, maximum function value, and again 100 points. So let's visualize that. So let's just plot some random red crosses. And to see them, we actually need to call the function with FAB. So function minimum will be our zero line in this case. And function maximum is something like around 2. Let's put it like that and generate. Let's start with 10 points. By running this, we can see we have successfully generated random points inside of our bounds. Just to confirm that they are not going outside, let's increase maybe to 1000 and see that yes, they are pretty much bounded by our invisible rectangle bounds. Well, actually, it should not really stay invisible. We can define a function draw rectangle where we can provide two set of points, the higher left point and the lower right point. And then let's draw 4 lines. One will be the vertical on the left side. So it's from y1 till y2, like a black line. Then the vertical right line. And we need 2 more horizontal lines from x1 to x2, starting with y1 till y1, and same goes for the second one. So now let's call this function and provide 2 points. The first point is the top left, which means it's a by x and maximum f value, which was 2. I think we need to extract it. Yeah, let's extract it as variables. So f min will be 0, f max will be 2. Let's use those instead of these values. And b and f min. Okay, let's run this. Okay, now we can visualize our rectangle much better. So now indeed we have confirmed that all the points are bounded by this rectangle, and now our goal is to calculate how many are under the curve. Let's extract points under, and let's go over all of the point pairs. Let's zip the x and y values together. And to understand if the point is under the curve or not, we can calculate what is the function value at that random point. So we can, for example, take function f from the x value that we have just generated. And if this value is larger than the point we are generating, it means that it's under. And we need also to take the x and y values. And now we would like to also visualize that, but to do that we need to unzip the values first. So let's extract the x points that are under by taking only x values for all the pairs that we have inside our points under. So we can just ignore that value, and the same thing we need to do for the y values. But now we need to extract the y value. Okay, let's plot all the points as red and plot the points that are under as green. And now you can see we successfully have extracted all of the points that are under the curve. So now we have everything to perform our calculations. First of all, we need to find how many times points were under the curve. So let's define this n under. And it's quite easy. It's just the length of our array points under. The total number is also available. It's just defined here in the function. So how many points we have sampled. Now we need to find the whole area of the rectangle. Area of the rectangle is just one side width times the height. And to calculate that, we need to take how many times it was under the curve divided by total number of samples. And now that we have everything, we can return the result. So our area under the curve is the probability or the ratio of how many points are landing under the curve times the rectangle area. So in other words, we're saying that we are taking the part of the rectangle that we have calculated to be under the curve. So now for debugging, we have kept our plotting inside our function. Let's extract it because it will slow down our calculations, because we will need to see how on average this function performs. Because of that, let's return all the points that got generated and the points that were under the curve, which will allow us to extract this part of code and have it as a separate plotting steps outside the calculation. But we now need to store this. So we will have the area or the integral value first returned, then the x and y values of all the points, and the zipped points under the curve. Of course, we should align so it be specific and in the same format, but not for now. Okay, now I can run the code. I can see everything still works. Just to see the impact, let's maybe downgrade it to 10 points. And of course, the area number does not tell me anything if I don't know the true value to compare to. So in this case, the true value for our function in this interval is just 2 pi. And now we can calculate the error. From the true value, we can subtract the value that we got. But I'm actually more interested in relative error. So I want to have an absolute value and see percentage-wise what is the error. So how hard? Is it 10% error? Is it 100% error? Is it just 1% error, etc.? And let's output the exact value that we got. So it will be the I. Then let's output the true value and let's output the error. And let's multiply it by 100 to get it in percentages. And let's output only two numbers after the comma. And we got our first results. By sampling 10 points, in our case, it was like 4 were outside, 6 were inside. We got on 20% error. So the original value was 6.28 expected, and we got 753. Of course, this is a random process, so every time we run this, we can get different results because we are taking two little samples. If we increase to that to 100, we can see the error right now is 6%. Let's repeat that, 2%, 20%. Wow, still bad results after 100 points. Let's take 1000 points. 1% error, 0.4% error, 1% error, 2% error. But of course, this is a non-deterministic approach. So it means we can have a bad luck and get worse results, or we have very good luck and have very great results. What actually we want to evaluate is how on average it performs. What is the spread of error? So what would be the expected error if we are running this algorithm? And only way to find out is to run it multiple times and see the averages. To make things cleaner, I removed all of the things that are related to plotting and left only necessary things. So I have left the function Monte Carlo with only the calculation parts. I have left the function definition, the input parameters, and the true value that we are expecting to receive. So now my goal would be, for example, to take 100 samples and see how on average it would perform between, for example, 10,000 attempts. So let's collect the results of all of the iterations. So let's go and call Monte Carlo for this function a b, minimum function value, maximum function value, and number of the samples for each time in the defined range. And what I need is actually to calculate also the errors, because this is what we are interested in. We want to calculate the average error. So we'll go over each result and we will subtract the true value to see the difference. Of course, the difference can be both ways. So we take the absolute value and we are interested in relative error, so percentage wise. Let's divide it by the true value and multiply by 100 to get the percentage. Okay, we have an error. I had actually a typo here. Instead of sin, we need to have here a pi. Okay, and let's print those errors out just to have a glance what's happening there. So you can see we have an array of different errors, and of course, those numbers pretty much does not tell us anything. So now we can start to analyze these errors using, for example, average, the mean, max, mean value. But we need to be careful with those because there is always some outliers. We can be very unlucky with some of the values, and ideally, instead of just having a mean value, we'd also want to have like the standard deviation. We want to see how spread is from the mean error. So is it on average closer to the average value, or it's spread out whole interval? And for that, we, for example, just can analyze a histogram. We can provide errors inside a histogram function. Histogram splits the interval into smaller buckets, so sub-intervals, and counts how many times a point has landed in that bucket. So in our case, if we had 10,000 runs, it means 40% of the points has landed inside the 0.5 bucket. And if it would be interesting how likely it is to have a bad case scenario from like 20 to 30%, we can see that maybe it is together under 1,000, maybe under 10% of our all cases. But still, it's a probability. But there is also another way how we can look besides the histogram. We can use box plot. So in this graph, we pretty much can see the same thing. So here we can see the most of the items are located in this pretty much box. So it's from some sort of 2% to, I don't know, 12%. Then we have our spread. So these lines are basically saying how wide is the spread. And there are some outliers basically saying that it's very little. So they're outside this range. So we could consider them as outliers. So actually we could also hide them. So we can take and show flyers and set it to false. Orange is our median, but I would also like to see the mean value. So I can enable the mean line. And I also need to show means parameter. Basically what now we can see that green is the mean and this is the median, basically saying which was the most common value. So now if I increase it, for example, to 1000 samples, so by just looking at this chart, I can say that on average by using this method, I can get an error between 2 and 3%. Worst case scenario, I can most likely get a 7% error. Best case scenario, of course, I can get near zero. So again, it just highlights how effective the method is. Just by taking 1000 points, on average, I will get 2 and 3% error on this function. And you can see by increasing our magnitude of the samples, the error drastically drops down. While it performs quite well, it is not the best variation of Monte Carlo integration. Actually, there is another way. Okay, let's step back and start from the beginning. So our goal is to find some sort of area that can be expressed by this integral notation. So we can actually express the same area as a simple rectangle. We just need to find proper width and proper height, so when they are multiplied, would produce the same original area as was under the curve. Now in our case, the width is easy. We can just take the length of the interval, b minus a. So we are left with the big question, what should be the height? And actually we can easily solve that. We can take the equation, rearrange the terms, and see that area divided by width will be height. Let's plug everything that we know into the formula. In the formula, we have on top an integral, basically an area or sum of our all function values, divided by the interval length. Basically speaking in math, it represents a mean value, the average value of a function. But okay, how it can help us to find the integral? Well, let's play with this equation around. So let's put the integral on the left side and everything else on the right side. And now you can see, following from this equation, the integral can be calculated by multiplying function mean times the interval length. But how do we find the mean value? We don't know the integral, there are infinite many steps, it's just complicated. Well, actually that's quite easy. Instead of getting exact value, we can estimate the mean. We could pick enough random points between a and b to calculate the average of the function. More points we get, the more precise the average value is. So it means that if we estimate by picking random values the mean, we can estimate the integral. Plug our estimated mean back to the equation and solve for the integral. And no fancy calculus is needed, just a random sampling, a bit of multiplication, simple, elegant. So yes, you have heard it correctly. To estimate the area under the curve of any given function, it is enough to estimate the function mean. Let's see how we can implement that and how it compares to the random sampling. So here we can just define again our Monte Carlo mean variation. Let's input a function, an interval in which we are interested in, and again, number of points. And everything that we need is just to sample random points in the interval between A and B. So X will be NP random uniform between A and B, and how many points that we need. And now we don't need to check if the point is under or below the curve. We can just calculate the Y values at those X points. So we now have sampled random points on the curve. And now our goal is to calculate the average, the mean. So function mean can be either calculated by you summing all of these Y values dividing by n, or we can use NumPy's built-in mean function and provide our Y values. And now the integral value can be calculated by multiplying function mean by our interval width. And let's just bring and output the same output that we had previously. So let's calculate the error by calculating the relative error and outputting the value that we just got, the value that we expect, and the error in percent. And that's all. Let's call it and see the results. Using 100 points, we have received an 11% error. We can rerun again that, 1% of error, 8% of error, 9% of error. And of course, let's run it many times to estimate it properly and compare to the previous method. So you can see the results are pretty similar to the previous ones, but there is only one large difference. This method was much simpler to implement and it's much faster. And actually that's not all. Before the sampling, we could analyze the function and see what is the distribution of points and generate random values by that distribution. And of course, this sampling idea is not only limited to the integration. For example, in the rendering, when you're rendering a scene, there are many light bounces. So instead of calculating each individual light bounce, we can take enough samples to estimate the lighting of the scene. I'm very thankful for all the support and the feedback that you left on the short version of this video. It really showed that this kind of content is interesting for you, and it also is interesting for me. And also let me know if there are any specific topics that you would like to see here. But for now, leave a like, subscribe so you don't miss next video, and as always, keep coding, and I see you next time.